So the first special function we'll look at is the gamma function. And this can be thought of as a generalization of the factorial function. So the factorial function, as you know, just works on integers, 3 factorial, 3 times 2 times 1, and so on. With the gamma function, you can now say what 1/2 factorial is, for example. Gamma function looks like this. As you can see, it's one displaced from the factorial function, in the sense that gamma of 3 is actually 2 factorial, gamma of 4 is 3 factorial, and so on. Anyway, so what is it? Well, it's defined in this way. It works for complex z as well as real, but we'll only talk about real z. It's defined in this way for real z greater than 0, but in fact you can define it for other values. You can define it for values of z below 0 as well. We'll see how to do that a bit later. This integral only converges if real z is greater than 0. For values of z less than 0, then there's another way to define it. There's actually another way you can write it down, which I just mentioned for interest. It can also be defined in terms of this strange looking infinite product, where little gamma is a special constant, which is used in higher applied maths. But the advantage of this product formula is that it's immediately obvious that you have simple poles at z equals minus n, where n is any positive integer. So that's actually what you're seeing here. You're seeing poles at 0, minus 1, minus 2, minus 3, and so on. Obviously you have a pole here as well. 1 over z gives you a pole at 0. Okay, so properties. The fundamental property is that, which makes it like a factorial, is that gamma of z plus n, gamma of z plus 1 is equal to z times gamma z. So it's just like the factorial function, except with a factorial function, obviously n factorial is equal to n times n minus 1 factorial. So they sort of differ by 1. To see this, it's very straightforward. All you do is you replace this, you put z equals n plus 1 in here. So you replace this by z plus 1 and you replace this by z, and then you integrate by parts. So if you can integrate by parts, you want to integrate the e to the minus t, and you differentiate the t to the z to give you t to the z minus 1. So if you, t to the z minus 1, which will end up being gamma z. So it's very straightforward to do. There's also this formula, which is rather more complicated to prove, and we won't. But also very useful. Reflection formula, in the sense that it's z and 1 minus z, so there's some sort of symmetry about z equals 1/2. Duplication formula, okay, duplication because it's gamma 2z in terms of gamma of z, and gamma of 1/2 is something we'll work out a bit later. So this one, is a generalization of the previous result. Again, somewhat complicated to prove, so we won't do it. Stirling's formula, which also works obviously for factorials, is a way of saying what the factorial or the gamma function is asymptotically equal to as n gets large. So this is a convenient formula, basically because n factorial is actually rather difficult to deal with. It's much easier to deal with these things if you're sort of working out things like derivatives and so on, or seeing how things tend to for large n. So gamma 1 equals 1. This is straightforward to arrive at via the definition. As we said, gamma n plus 1 equals n factorial. Again, follows from this result here and the fact that gamma 1 is 1. Now finally we get to what gamma half is. Well, it's root pi, from which you can work out what half factorial is, if you like, from this formula. So as we mentioned, this integral formula only works if the real part of z is greater than 0. But what happens if it's negative? Well, it's very straightforward. All you do is apply 3.4 in reverse. So you put a half in here, and you put minus a half in here. That will give you minus a half times gamma of minus a half equals gamma of plus a half. Okay, so rearranging that gives you this, and gamma of a half is root pi, so we end up with this. So any half integer arguments of gamma end up being multiples of root pi. Now, the whole point of the gamma function is to allow you to do integrals like this, or integrals that can be converted into this form. So, for example, if we make the substitution t equals u to the mu into this, and see what we end up with, then it's straightforward to show that this is true. What would actually happen is, if you were given this integral, it sort of works the other way around really. If you're given to this integral, you would make substitution t equals u to the mu to get it into this form, and you'd end up with you'd end up with z being replaced by p over mu. Anyway, I'll leave it for you to work through. So very closely related integral is the beta function,